Hey everyone. So I finished the last video with a brief discussion of permutations and combinations. And just to reiterate, permutations describe how to count the number of ways to arrange objects, kind of taking into account where the ordering um, of the objects matters, right? So another way to thinking about this would be sampling without replacement. If we have, for example, set A, B, and C, one possible permutation would be the order ABC. Another permutation would be ACB or BAC and so on. And you can think of this as either different orderings or different times where we sample without replacement. We sample one of the letters first, then sample one of the remaining letters and then sample the last letter, so to speak, right? So that's just one way of thinking about this, okay? And then we have combinations, and this is basically the ways to select objects without regard to their arrangement. So here the order doesn't matter, it just matters what types of objects we select, right? So combinations, or I guess the easiest example to think about could be, thinking about how many possible combinations you have if you deal a deck of cards and you receive 10 cards or something like that, right? So the ordering of the cards doesn't matter, but how many different combinations do you have, and how likely is it that you get 4 aces or something like that, right? So as soon as we have something, an arrangement like that, where we're thinking about the number of possible arrangements and combinations where the order doesn't matter, that's when we kind of think about n choose k rather than thinking about permutations, okay? And so now we're going to look at two fun examples to kind of illustrate how we work with permutations and combinations. And the first example that we're going to talk about is the birthday problem. And we're going to look at this problem from two different perspectives, or with two variations. The original problem, or the original question, is how many people do you need in order for the probability that at least 2 people have the same birthday to exceed 0.5, right? So how many people do you need in a group that you have at least more than a 50% chance that 2 people have the same birthday? And it turns out that if you kind of were to guess, or if you haven't read the chapter yet, and were to guess, often people's intuition is kind of systematically wrong, in that sense that a lot of people under or overestimate how many people are necessary to achieve that. The number is actually surprisingly low. But how we can compute it, we need permutations, right? So, and this is one example where the way to kind of compute that probability is the simplest way to compute that probability is by focusing on complementary events, right? So rather than directly computing the probability that is asked for here, how many people, the probability that at least 2 people have the same birthday to exceed 0.5, we can also just look at the probability of k people having different birthdays, and then take one since the complement of that is that at least one person has the same birthday as another person. So the probability that we're actually looking for is 1 minus the probability of k people having different birthdays, right? And so that's a little bit easier to kind of handle and to compute. So how do we then compute the probability of k people having different birthdays? Well, there are 365 days in a year, and so this is a permutation problem, and we basically want to think of this as sampling without replacement. So we have 365 possible days in a year, and for each person we sample 1 day, so the first person basically has 365 possible days. Person 2, of course, can't have the same birthday as the first person, so there are only 364 possible birthdays, and so on, right? So that's 365 permutation permute k to kind of select k individuals with different birthdays, divided by 365 to the power of k. Of course, those are the total number of possible birthdays, so to speak. Okay, that's that's 1 minus 365 factorial divided by 365 to the power of k times 365 minus k factorial. And that's just plugging in the formula for permutations, right? Now what we can do is we can plug in, and in the chapter you'll see some R code to kind of do this for different numbers. We can now plug in different numbers for k, and then we arrive at and compute the resulting probability. And and if we do that, we'll see that as soon as we have 23 people in a room together, the probability that at least 2 have the same birthday is 0.507, so exceeds 50%. We can also think about this problem in a slightly different way, just to give you an additional problem to kind of think about. Imagine rather than having people all in the same room, you could also think about lining them up in a row, and then you go through them step by step, and you check whether they have, whether each individual person shares a birthday with another person who was already ahead in the line, right? So people line up, the winner is the person who shares birthday with someone ahead in the line, right? And so suppose this was a game and you wanted to be the person who is the first person who shares a birthday, then the question could be, where in that line should you kind of place yourself strategically, right? So how many people do you need in order to maximize the probability that at least that the last person in the line wins, right? So it's related, but it's not exactly the same type of problem, but it's nevertheless still a problem of permutation, right? And the way we can compute this probability is to basically just compute the probability of k minus 1 people having distinct birthdays, and the kth person shares a birthday, right? So the first part is of course similar to what we kind of already computed, which is k people having different birthdays, or now k minus 1 people having different birthdays, so that's 365 permute k minus 1 divided by 365 to the power of k minus 1, and then this has to be multiplied by the probability that the kth person then shares a birthday with one of the other people, and that's of course k minus 1 divided by 365. We can then kind of rearrange this, multiply this out, and we end up with that this formula. Similar to the example that is shown in the chapter, we can now kind of plug this in, write this as an R formula, plug in different numbers for k, and then look at the underlying kind of resulting probability to be the first person who shares a birthday with someone ahead in the line, right? And the code to do this is here. Birthday.line is a function that is just a function of k, so the number of people in that line, including the last person. And all we're doing is we're basically taking this formula here, this equation that we have, and just program that in R. One thing, and that's a general piece of advice if you're kind of working with permutations or combination or combinatorics in general, one thing that is very common, because these numbers 365 factorial or 365 to the power of k and so on, they become incredibly large, right? So we have a very large numerator, very large denominator, and that can easily, the numbers can be so large that your computer cannot handle them easily, right? So one way to get around this is to basically just take the logarithm of the numerator and the denominator, or take the logarithm of the fraction. If you take the logarithm of the fraction, that's equal to, if you remember your logarithm rules, that's equal to the difference of the numerator minus the denominator. So the fraction is replaced by the difference. And then we compute that, the difference in the logarithms of the numerator and the denominator, and then after computing that difference, we then take the exponent, right? So because the very large numerator and the very large denominator, they cancel each other out to some extent, essentially. The resulting number is, of course, a number between 0 and 1. And so as soon as we take that exponent, we have, a probability. And so that kind of helps us avoiding these really, really large numbers. And that's why we have here, rather than factorial as the command to compute the factorials, we have L factorial. So that computes the logarithm of the factorial, right? So if we look at the original fraction, we have 365 factorial times k minus 1. And of course, if we take the logarithm of that, that's the 365, the L factorial of 365 plus the logarithm of k minus 1. And then we have for the denominator the logarithm of 365 minus k plus 1 factorial, and then k times 365, right? So here we have the denominator k times log 365 plus the logarithm or logged factorial of this term, and then the numerator, as I said, the logged factorial of 365 plus the log of k minus 1. Then we take the difference because those are the basic logarithm rules, and then we take the exponents to get back to our percentage or to our probability, and then we return this result. We can now plug in two numbers from 2 to 60, and then basically just save the probabilities as a new object that is the result of that function from 2, where we basically compute the probability from for values of k from 2 to 60, and then we plot this in a basic dot plot. Okay, and this is the result that we see. We see that the probability, of course, starts somewhere here. The first person, of course, has a probability of 1 over 365. And as you go further down the line, the probability of being the first person who shares a birthday with one of the people ahead of line increases the more people you have, reaches the maximum around at 20 people, and then of course later on decreases. Why does it decrease? Well, because the probability is then becomes high enough that someone before you already shared a birthday with someone else, right? So on average, the highest probability to be the person, the highest likelihood to be the first person who shares a birthday with the person ahead of you in line is then 20. Okay. The next example is another fun example of the time when Schwarzenegger was a governor in California, and and this is also discussed in the chapter. And in one of his signatures, or one of his messages to bill that was passed by the Democrat-controlled state Senate, or the state assembly, Arnold Schwarzenegger refused to sign the law and returned the bill with a message that stated the following. You can pause it and read it. I'm not going to go through the entire text, but essentially he just says that he refuses to sign this law, returning this law, because there are other more important issues. But the important part is you can also look at the first letters in that message of the main paragraph and the second paragraph, and you get an idea what potentially upset the legislators in the state assembly. Once people kind of noticed that, of course there was a little bit of controversy about this, and Schwarzenegger's spokesman, Aaron McLear, said, "Oh my goodness, what a coincidence. I suppose when you do so many vetoes, something like that might happen." This got cut off, I'm sorry. But of course the question is this a reasonable, responsible defense? Is this, how likely is it that, just by pure coincidence, you have a message like this as part of this as part of these paragraphs, right? And so the good thing is we can answer that question. We can say how likely it is that it might happen, you know, just by pure chance. So how do we do this? This is a question, or this is a problem of combinatorics. The order, in the sense that we have, suppose the message was given, and the question is not the way we conceive of this problem is the message was there, and we can think of this as the line break. The question is where the line breaks in the message happen, and so where a new line starts and what the letter of the new line is, rather than, you know, thinking about probabilistically what the message itself was, right? So take the message as given, and the question is just where the line breaks are, right? So the original question here is, the governor gave his veto message to his secretary, who then typed in her computer but hit the return key at random. That is, the 85 words from 4 to time were divided by random line breaks into 7 lines, which each with at least one word. Assume that every way of breaking the lines was equally likely and the total number of lines is fixed at 7. What is the probability of the coincidence happening? All right, so if we want to do that, of course, we need two components. First, we need to see that there are 84 places into which these 6 line breaks can be inserted, right? Because we have 85 words from 4 to time. Those are 84 or 85 words, and so you can think of this as again basically a question of dividing this into, since we have 6 line breaks, we could think of this as dividing this all the words basically in 6 different, or in 7 different groups essentially, right? So if we kind of want to count the number of possible ways, or the number of possible ways of how we can arrange those line breaks, we can basically think of this as a combinatorics problem, where we basically choose insert 6 line breaks at 84 different places, right? But the order of the line breaks itself, if we think about placing these line breaks at different locations, the order of the line breaks is not what matters. What matters, you know, what matters is basically just where you place each individual line break, right? So suppose all the 85 words are kind of held constant, and you're kind of sampling where you kind of, in each of those gaps between the words, where you put those line breaks, right? And so then the line breaks themselves, you know, the way you kind of think about throwing the line breaks into those spaces, the ordering of that itself doesn't really matter, right? So that's why the order, in that sense, the order doesn't really matter in which you kind of assign these line breaks, right? So in order to count that, that's 84 choose 6. So if we plug that into the formula, we get a very large number, 4.1 times 10 to the power of 8, right? So a lot of different possible combinations. Now the question is, how many possible ways are there that kind of result in the message that we see? And there are essentially, if we go through the message itself, there are 12 different ways that would result in the pattern that we observe, right? So we could say the first line, of course, is here, and then we could have a line break here, where it is, but essentially we could also oh yeah, for the first first word, there's no alternative line break, but then we could have a line break at come, consideration, care, so that's 3 different options, and then we have kick, that's just one. Yet and year are two different alternatives. Overwhelmingly, and so on. Okay, so essentially, yet and year, overwhelmingly off, and then unnecessary is just one. Okay, so if we kind of look at all those different combinations, those are 12 different ways of kind of arranging this message in the way to kind of have this additional message, right? So that means that what is the probability of this happening by pure chance based on this kind of model of the underlying process? That's 12 divided by 4 times 10 to the power of 8, so that's 2.9 or 3 times 10 to the power of minus 8, right? So that's an incredibly small probability. So in essence, kind of assuming this data generating process, it's extremely unlikely to have a line break arrangement of the sort that we have here by pure chance. We can modify this question even more and say, okay, what about we include the initial first sentence as well and take that into account, and that means that we now have basically 94 words that must be divided into 8 lines. Basically we're including this sentence as well, and that of course increases the possible the total number of possible arrangements, and therefore but it also increases the number of it also increases the number of arrangements that result in the pattern by multiplying them by 2, because we can either start the first line with 4 or fact, and then we have 24 divided by 9.5 times 10 to the power of 9, so an even smaller probability, right? So taking into account the first sentence reduces that probability even more. Okay. So after going through these examples, I'm going to take a break here and then talk about conditional, marginal, and joint probabilities in the next video.